Now we want to take a look at the divergence theorem. Now the divergence theorem is much like Stokes' theorem. It allows us to see a relationship between certain integrals, and again we can think of it as the big brother of Green's theorem. Green's theorem said that the flux across a curve, a closed curve, is related to the area of the region by some factor, and that factor happens to be the two-dimensional divergence. Now, in the divergence theorem, we have a very similar scenario. We're taking a look at a surface integral here, a flux integral. Now, if this is a surface that is completely enclosed, then it is related to the triple integral according to the divergence theorem. Now, to show how to employ the divergence theorem and to show that it actually is true, we're going to take this vector field and look at the flux of the vector field across the surface that's given as the sphere. So that is an enclosed surface. We're going to do the surface integral. Now we'll go through the mechanics of this because we've already done this several times. I'll go through it a little bit quicker. The parameterization of the sphere looks like this. We do the derivative in the u direction, the derivative in the v direction, and find the cross product to get the normal vector. Now we need to do the dot product of f with the parameterization substituted in, and the cross product of RU and RV. Now that just comes out to be this. Now we want to integrate that over the surface. So we need to describe that now. And since we already have the parameterization of this, we can do the integral using our parameterization. Now the idea, of course, is the divergence theorem says instead of doing the process we just did, we could do the triple integral of the divergence of f if we can just describe the volume of the solid. So we'll do the divergence of f. Now this is pretty easy to do since we've got x equals 0. The derivative of that is still 0. Y equals 0. The derivative of that is 0. The derivative of z is 1. So we come out with a divergence of just 1. And here's the triple integral. So now all that remains is for us to describe that solid, the sphere, with a radius of 2. Well, since that is a sphere with a radius of 2, and since the integrand is a 1, then really the triple integral is nothing more than the volume of the sphere. We can use algebra to find that. Now here's a little more challenging one as far as the integral is concerned. The solid that's described here, as you can see, has a top that is a paraboloid. The sides are the cylinder. Now we can't see the bottom, but the bottom, as you can probably imagine, means the bottom of that cylinder, which would just be a disc. Now, to do a surface integral, we would have to do a surface integral for the top, surface integral for the side, and surface integral for the bottom. So we're thinking instead of doing those three integrals, it might be better to just do the divergence theorem, since it is an enclosed region. The divergence, again, is pretty easy to compute for this one. Comes out fortuitous. The derivative of xy with respect to x is just a y. The derivative of negative 1/2 y squared would be a negative y. And the derivative of z would be a 1. So again, the divergence comes out to be a 1. I wouldn't count on it always being quite so nice. However, to evaluate this triple integral, we will use cylindrical coordinates. Now, in cylindrical coordinates, you can see the z would be always going from bottom to top. And so that would be going from the disk, which is at z equals 0, to the top, which would be z equals 4 minus r squared. So our z's go from 0 to 4 minus 3r squared. And the r, since it's a circle with a radius of 1, will be going from 0 to 1. And then we want to go all the way around to get the entire figure. And so here would be the integral that we would need to evaluate. Now, I think that would indeed be better than evaluating three different surface integrals.